Hello everyone, my name is Eric Hillsberg. I'm the product marketing manager responsible for the aerospace products at MathWorks, and I've been here for 3 years, joining after graduating from the University of Michigan with a degree in aerospace engineering. While at MathWorks, I've spent much of my time creating videos, demos, white papers, and more to communicate key technical concepts to our aerospace customers. Today, using a VTOL UAV example from our documentation, I'll be demonstrating what a modern flight control design workflow looks like in MATLAB and Simulink, and a couple advanced control techniques that can be used to reject disturbances and improve system performance. The workflow I'll share with you today will help you save time and lower the risk of hardware loss through development and testing of your control systems in simulation. Our example platform is a tilt-rotor VTOL modeled with aerospace block set. The front rotors tilt to enable both vertical and forward flight, allowing for transition between hover and cruise modes. For this session, we're going to focus on just the hover mode, using a representative mission profile to drive our control design. When I run this model, in the bottom left, you're going to see a trajectory plot, and on the bottom right, you'll see an animation of the tilt rotor showing the orientation and rotor direction, similar to what's on screen right now on the right side. We're going to start with a nominal mission. The VTOL takes off to a commanded altitude, maintains that altitude, and navigates several waypoints. It's going to land roughly 100 meters from its starting location. In this ideal scenario, with no external disturbances, our baseline controller performs as expected. However, real-world operations are rarely ideal. Luckily, Aerospace Blockset enables environment modeling. To save a little bit of time and make the results clearer, I'm going to switch to slides containing a recording, the simulation data, and a flight plan. Don't worry, we'll come back to Simulink in a bit. So I'm going to run this exact same simulation, but this time we're going to introduce a wind gust partway through the mission. The simulation is the exact same mission profile with that large wind gust westward and northward introduced. We can take a look at some trajectory and error plots so that we can see them more clearly. You'll notice that the vehicle deviates significantly from its planned trajectory. This is a common limitation of traditional PID-based controllers, which can struggle with large and unpredictable disturbances. In this presentation, I'll show you how MathWorks tools can help you model your aircraft and control system, and then we'll introduce disturbances to test your system under conditions that they may face in the real world. Finally, I'll show you how you can introduce more complex control algorithms such as Active Disturbance Rejection Control, ADRC, and Model Reference Adaptive Control, MRAC, which offer improved disturbance rejection and handling of uncertainties. Let's see how ADRC performs under these same conditions. With ADRC, the VTOL maintains its trajectory despite the wind gust, demonstrating effective disturbance rejection. And while it doesn't cover everything, we can use the average error from the mission plan as a score for each of our control designs. You'll notice that in the bottom left. For this exact model of our aircraft, the look-ahead distance is 5 meters. You don't need to necessarily know what that means, just that less than 5 meters is a very good starting point for our controller. Before we dive into our model, I want to do a quick review of model-based design to put this presentation into its proper context. We describe model-based design as the systematic use of models throughout the development process. And there are two major components: modeling and automation. Modeling with simulation and analysis to try out new ideas and give you fast, repeatable tests. And automation of coding and verification to take out manual steps and reduce human error. In the presentation today, we're going to focus primarily on the value of modeling your systems. Let's do a quick agenda of what we'll cover. So first, we'll do plant modeling in Simulink, mostly focused on our aerospace block set. Then we'll take a look at our control system architecture, as well as some auto-tuning capabilities from our controls tools. Then we will model some disturbances using the aerospace block set's pre-built blocks and navigation toolbox as well. And finally, we'll talk about the advanced control techniques like ADRC and MRAC, which can be used to mitigate these disturbances. To make it easier to follow along on the side, I have created this legend for us. So starting off, what are the options for plant modeling inside of Simulink? Well, first, there's obviously base Simulink. This is going to require the most effort to build up your model. If it's done right, it can give you the most control over every aspect of your model, but it can quickly lead to large models that are difficult to understand, maintain, and validate. Then there's homegrown tools, which can help take some of that burden of modeling off of your shoulders. But it still requires someone in the organization to maintain and validate those models. That's where Aerospace Blockset comes in. It provides much of the common functionality you need to model your systems in a logical grouping, allowing you to select the ones you need without building and maintaining each one individually. Our VTOL model is built up from first principles using the Aerospace Blockset. So before we get into the model itself, I want to give you a better idea of what the important building blocks are. The heart of any simulation model are the equations of motion. We're going to be using a 6DOF, 6 degree of freedom model, but depending on your needs, we also have point mass and 3DOF blocks. These blocks take in the forces and moments and output the states with rigid body assumptions. And while we won't use this today, they also allow for modeling of variable masses and inertias. Then we have standard environment models like the ISA atmosphere model, some magnetic field models, as well as things like wind models like Dryden turbulence. We have some utility calculations like coordinate transformations, unit conversions, and dynamic pressure and side slip and incidence angles. Last and certainly not least, the force and moment calculations from our aerodynamics and propulsion systems. And these are major building blocks of what we're going to use today. Many VTOL aircraft, including our model, employ both fixed wing as well as rotors. So we're going to incorporate both into our feedback loop with this 6DOF block. So let's go into the model and take a closer look. This is our top level view of the model, and inside of this digital twin system is where our dynamics model lies. So as I said, we have our 6DOF at the heart, and we feed back these states in order to calculate our forces and moments. Inside of this subsystem, we also take in our actuator and control surface deflections in order to calculate these forces and moments. So let's dive into this forces and moments subsystem to take a closer look. All right, inside of here, we have 4 main sources of our forces and moments, which are then summed back together over here. And then they are output. First, along the top, is our aerodynamic forces, which takes in environmental info like the wind and air density and the control surface deflections, and then some state information. This is where our fixed wing portion, the aerodynamic forces and moments block, lives. So why don't we go into here? Before we can calculate our forces and moments, which is inside of this subsystem, we also need to compute some air information. Inside of this subsystem is where we make use of some of those utility blocks I was talking about. So our dynamic pressure, as well as our incidence, side slip, and airspeed. Popping back up into here, inside of this subsystem is where we actually make use of our aerodynamic forces and moments block. That's this block right here. So what we're doing is inputting the coefficients, the dynamic pressure, and we're making some simplifying assumptions about the center of gravity and center of pressure, but the block also takes those in and then can calculate the forces and moments. What's really powerful about this is you can use both wind and body reference frames, and you have a lot of ability to input different coefficient calculations. Right now, we're actually just using some literature-defined coefficients, but you can reach out to your Aero team and they can provide you with either some lookup tables or some equations similar to the ones that we've used inside of this subsystem. And there's also the alternative of using the digital DATCOM. So if you have a digital DATCOM model of your system, you can take this and replace basically this entire subsystem with just that block alone and be able to model it. Great. So these are where our aerodynamic forces and moments are calculated. Let's hop back up to that top level forces and moments subsystem to look at the next one, which is our propulsion, which is across this middle here. The propulsion system takes in the air density as well as our actuator commands and some states. This is where our rotorcraft portion, the rotor block, lives. So let's dive into this subsystem. In here, we actually have 4 rotors which are modeled separately, but they all take the same inputs, and this keeps our design very modular and makes it very easy to adapt. For instance, if we wanted to create a new motor, for example, if we wanted a pusher motor for our new design of our VTOL, we just copy and paste, change some of the names here, add them up into the sum of forces and moments, and that's it. Really simple, really easy, and this is great for the design exploration phase, especially with unset business models of the VTOL and advanced air mobility market segments. Right, so if we look inside of this rotor assembly, which is the same for each of these different 4, there's going to be the rotor block as well as some geometry calculations. So just basically taking the rotor and moving it to its position with respect to the center of gravity. All right, so let's move back up again to our forces and moments subsystem, where we have our 2 final sources. We're not going to spend much time on them, but just to let you know what they are, it's gravity and a very simple ground contact model. With this, we can get a really solid baseline model of the aircraft, and it makes it easy to update our model when more detailed data becomes available, or if there are changes to our aircraft, like the pusher. Let's hop back over to our presentation. Now let's talk a little bit more about our control system's architecture. This is a very hierarchical control system. It needs to be able to adapt to different modes. So we have both a multi-copter controller as well as a fixed wing controller, which feed into a scheduler, which actually output the commands to the system itself. These take in both a plan as well as the actual states of our system, but most importantly, they take in a flight mode, which we use to switch between and actually handle all of this scheduling. Because we're talking about the hover system of our VTOL, we're going to take a closer look at the multi-copter controller subsystem inside of here, where we have another set of hierarchical controls. So we have a horizontal position controller, which controls our position in the XY plane. So we feed it a plan, as well as that state information, and it outputs the forward tilt commands, which allow us to move in the X direction, as well as roll commands, which help us move in the Y direction. This feeds into our attitude controller. So this takes in our states, as well as pitch and yaw plans, and that roll command from the horizontal position controller. Our pitch and yaw commands are actually supposed to be held at 0. This keeps it easier for our system to be able to be stable, especially with these newer designs. It's more difficult to be able to use quadcopter-like control algorithms. And this outputs our torque commands. Finally, we also need to take into account our altitude. So we need an altitude controller, which takes in the states and our altitude plan and outputs the total thrust that our system needs to stay at the commanded altitude. And we're going to dive deeper into the attitude control system, which is where we're going to be doing most of our changes to this model. So let's take a closer look at what that looks like. We're employing a cascaded PID architecture with 3 parallel loops using the control system's blocks that are built inside of Simulink control design. These are pre-configured blocks for common control algorithms, and these are really useful. The other control subsystems also have a very similar low-level architecture with position and then rate controllers. So if you'll notice, we have roll, pitch, and yaw, and then we have roll, pitch, and yaw rates for our controllers. This is what I mean by cascaded. So using our baseline controller, we can actually see the results of a simulated mission, which is what I showed you at the beginning, and we're going to be using this to compare our performance. The control system performs pretty well, but we can take a look at the auto-tuning workflow and see how we can actually improve the performance further. So to do that, let's go into the model. All right. So along with all of those pre-built blocks, we actually have a lot of ability for built-in auto-tuning capabilities. There are a few ways to auto-tune your control systems in both MATLAB and Simulink. The first and most easy is to open up the dialog for a specific block like this P and push this tune button down here. This is going to open the PID tuner app. And this is great if you have a few controllers, and especially if you like to visualize the effect of changing your gains. Similarly, we also have some other GUI options, which offer you a little bit more control over trimming and linearization of your model. You can use the Model Linearizer and Control System Designer apps, which are inside of this app gallery here. And these are great ways to tune your system that shouldn't be overlooked. So if you're interested in learning more about them, please do reach out. But the workflow we're going to be using today is programmatic, which allows us to tune multiple controllers with a single script. The workflow itself is actually really simple. Because we've already configured our model for manual control, a simple choice is to set our plant to hover at 10 meters and use a snapshot method to generate an operating point, which we will linearize our system around. We're designing this hover controller, and we want our system to be linearized around a static hover, which is why we're choosing 10 meters. And we're also going to be doing that at 7 seconds, which is the time at which we reach that 10 meter mark. So that's when we take the snapshot. So let's dive into the helper script, which we're using to take a closer look at what I actually mean by that. So first, what we need to do is set up our linearization options. So that's what we do in this first section. Our linearization options first are to set a sample time. And what's important here is to make sure that our sample time is well below the intended controller bandwidth. We're also tuning our PID with goals. So we have the goal of a phase margin of 60 degrees and a balanced design focus. The other options are to prioritize reference tracking or disturbance rejection if it's possible to do. The next step is to loop through each of the controllers, working our way from our inner loop to our outer loop. So what I mean by that is doing the rates and then the position controllers. So we're going to do this for all of our roll, pitch, and yaw, as well as our altitude and horizontal position controllers. And we're going to be repeating the exact same process for each controller. So I'll just cover that once and you can extrapolate to the rest of them. So first, what we do is define our linearization inputs and outputs. Our linearization input is the input to the plant, input into the plant, not the input into the controller. So that would be the output here. The linearization output is the output of our plant. So that would be this signal here, the roll rate. Then what we do is linearize our system. That is at 7 seconds using the same options and input outputs that we just selected. Then we call PID tune at a bandwidth of 50, and we input our control options. And then we extract our gains. It's that simple. Let's head back to the presentation and I'll show you what the results of this actually look like. Just by running this script, we're able to improve our performance with little effort. In the bottom left, you can see that our average error is 4.3 now, lower from 4.5. And if you take a look at the plots on the right, you can see really where this difference lies. The position controller, especially in the X direction, is much faster. And so we're able to complete the commanded trajectory in much less time, and this actually is what is leading to the lower average error. The auto-tuning workflow is also really helpful. For example, if you have cross-coupled control design, or if you want to have more control over what you're trying to do, we have another function called systune, which allows you to have control over all of these tuning goals that are laid out right here. For example, for our fixed wing controller, we actually make use of this inside of the exact same example. So you can check that out afterwards in your own time. So we have our airspeed step tracking and our loop shape goals that we'd like to meet. And we can actually tune and check to make sure that we're doing that and make sure that our system is robust. We can also make use of the auto-tuning workflow for gain scheduling. And we have another example for this inside of our Simulink control design tool, and you can check that out after as well. It makes use of scheduling variables in order to automatically tune your gain scheduled PIDs. Now let's take a look at modeling of disturbances. As I said in the beginning, the real world is never as forgiving as what we've been assuming so far. So we're going to talk about the disturbances that we can introduce, test our controllers against them, and even auto-tune a little bit to handle that. MathWorks tools actually make this really simple. All we're going to do is inject into the loop that we've already built these disturbances. If we take a look at the Simulink model, inside of that subsystem with our weather model is actually where we're going to introduce these disturbances. So if we wanted to introduce a horizontal wind, we would introduce that inside of there. But how do we actually do that? Well, the way we do that is through variance. So we actually have variant subsystems, which are a simple model, which has no wind effects, a weather model, which has simple horizontal wind effects. And then I even have a disturbance model on top of that, which has discrete turbulent models as well as wind gust models, which we'll be using later. And we're able to switch between these with a simple variable flag like wind or disturbance and setting those equal to the value of the variant system we want to use. And what's really great about this is it allows us to switch between model versions without creating messy models or deleting our previous work. So let's see what happens when we introduce some wind and test our controller's robustness. So what I've actually done is auto-tuned our controller with this wind in the loop, and we can see what the results are. The wind is a constant 8 meter per second eastward wind, so it's pretty strong, but it is constant. And we can compare it on that exact same mission. And we're getting an average error of 4.56 meters, which is pretty good. And you can see there are some small deviations, and depending on your system requirements, those might be acceptable. Sometimes they won't be, but for most cases, I would say they probably are. However, some disturbances are impossible to predict, and a PID can't always be tuned to handle those kinds of circumstances. So let's talk a little bit more about the kinds of disturbances we can introduce with Navigation Toolbox and Aerospace Blockset in order to model these. First, let's start with Navigation Toolbox, where we can model our sensors as well as filter models. And this is great because you can model these based off of parameters of your real-world sensors from their data sheets, and you can compare how your system performs with different specs. And it also helps you save time and not have to maintain all of these different models. And then inside of aerospace block set, we have some wind and turbulence models, which can be really helpful when you're trying to model disturbances. So that horizontal wind, the turbulence models, and also discrete wind gusts. Let's see what happens when we introduce some noise with sensors and turbulence. So this is actually the baseline controller, again, running with noise introduced into this loop with our sensor model and the turbulence model. And you can see it performs relatively well overall, not too far off from when we have just wind introduced. But you can see there's this really big overshoot right at the beginning. And this might be enough for you to say, my system is not able to handle the disturbances it will see in the real world. So you might want to be able to do something different. And you can actually see with the average score, we're less than 5 meters. So maybe you say that that's okay. But what happens if we introduce a really large disturbance like the wind gust I showed you at the beginning? So this is actually a wind gust of 12 meters per second westward as well as 9 meters per second upward at their maximum. These are introduced over time because it's a wind gust, right? And we have this really big deviation that I showed you at the beginning. And the average error was actually over 7 meters. This is really big and almost definitely does not meet the requirements of the system, though it is possible they'll never face a large wind gust of this size. These disturbances are really, this disturbance modeling is really powerful. So what we can do is actually run a parameter sweep across the entire environment space. Like if we wanted to change the wind direction from 0 to 350 degrees in 10-degree increments with our horizontal wind model and test the robustness. And we can see we've identified some places where our control design might not be good enough. And this also allows you to test and rapidly iterate to make sure that you're meeting your design requirements. And you can also use a testing workflow with Simulink design or Simulink test harnesses, or it can be used in Monte Carlo experiments. This is a really versatile workflow. All right, so how do we actually handle these unpredictable disturbances? Well, over the last few years, we've introduced workflows for many data-driven control techniques in MATLAB and Simulink, which can be leveraged for this challenging control problem. Today, I'm going to present about just ADRC and MRAC, but I want to be clear, there are other solutions to these issues. These are good though, because they're great for disturbance rejection. That's why I chose them. Let's start with active disturbance rejection control, ADRC. You can think of it as a powerful extension to PID control. It's a model-free adaptive control technique, and it can be applied to plants with unknown dynamics or internal and external disturbances. And it actually has a comparable performance in terms of throughput and memory requirements to PID. So it's pretty easy to fit these on the same sized control systems inside, or same sized hardware inside your control system. They're very computationally inexpensive, and they work across a wide range of operating conditions. So how do they work? Well, first, the model is approximated with a gain and input to the plant. And then the total disturbance, meaning both the unknown dynamics as well as other disturbances, are calculated and summed into that. And this is done with an extended state observer. And this allows for the nominal controller of the simple model to be able to reject these disturbances unmodeled as well. How do we actually implement this inside of Simulink? Well, all I've done to get my performance is just replace the roll controller inside of that subsystem. The rest of those are remaining the same with their same PIDs. So what does this look like when we introduce turbulence and sensors? Well, if you take a really close look, you might not be able to see it on this plot, but the overshoot is actually not there when we introduce ADRC. You can probably see it a little bit clearer when you look at these. You can see that there is no overshoot. And this brings down the average error very close to what it was when we didn't introduce any noise. So ADRC is really powerful for being able to handle this kind of random noise, and it is able to reject it. ADRC is also designed to reject large disturbances like wind gusts, and I showed you this at the beginning, where we were able to take from our baseline of over 7 meters of average error back down to 4.5 and get really good performance. All right, so what about MRAC, Model Reference Adaptive Control? So yeah, this is a adaptive control method that you can use when you need to deal with systems that have changing dynamics, like losing a wing. So MRAC can handle these changes by learning control parameters online, meaning it automatically adapts the control parameters during the operation to make the system track the behavior of a reference model. There are a lot of advantages to this. For example, it's really good at controlling plants with changing dynamics and uncertainties, and it also works on unstable systems. So how does it work? Well, first, the desired performance is described by a reference model. In our case, it's a second-order system. Then feedback and feed-forward gains match the system behavior to the reference model based on an internal disturbance model. And a learning mechanism continuously adapts these controller parameters to estimate and cancel these uncertainties. How have I implemented this inside of our control architecture? Well, I've replaced all of them because this is a MIMO system. So the MRAC can also handle these really large disturbances like wind gust. You can see across this entire mission, the average error is actually down to 4.5, similar to the performance of the ADRC. So why actually use the MathWorks solution for these advanced controls? Well, rather than building out these control architectures yourself, you can use MathWorks tools like the pre-built Simulink blocks that will help you get your design and implementation much more quickly. We also provide code generation capabilities when you want to deploy your control algorithms onto embedded hardware, and we have some very efficient code generation. And the whole workflow that I've shown you today actually aligns with our bigger model-based design. So what's the value of actually using this model-based design workflow I've talked about today? Well, the traditional development process typically involves heavy investments in building physical prototypes, which is very expensive, time-consuming, and prevents rapid iterations. On the other hand, creating and simulating a virtual model enables much more complex design space exploration and continuous design improvement, and it's much cheaper, faster, and safer. The MBD workflow is the basis of this presentation. Model-based design helps restore balance and reduce overall costs by removing waste from creating physical prototypes and places a stronger emphasis on modeling and simulation, which enables you to spin your development cycles faster by rapidly prototyping and testing new ideas. What I want to leave you with is that this workflow is very easily adaptable. As your designs change, so can your model. As you decide on components like sensors, you can model their specific parameters. And you have the freedom to experiment with your systems, like using advanced control techniques in an environment where it's easy to test out your systems before deploying code onto the real thing and reduces the risk of hardware loss. Thank you all for attending, and I'd like to open it up for some questions.